Okay, so we've been talking a lot about interoperability, modularity, benchmarking, and like I said at the start of this workshop, our Compare project is trying to really unite these two concepts because we think that they benefit each other. So to that end, as a way to facilitate some of this modularity and benchmarking, we have been doing some development on some modular pipeline infrastructure that is attempting to aid in streamlining benchmarking. The vision for this is so that we have these interchangeable components such that as you're swapping out different components from a pipeline, that you can truly do that kind of side-by-side comparison that I mentioned in the beginning of the workshop, where the rest of the pipeline is standardized or at least held static, but you're changing out one or more components of it. And I'll just show this animation again of kind of an example of changing out grass planners or changing out embodiments. So just kind of reiterating from the start. To this end, we have been developing a pipeline infrastructure, and we call it infrastructure because it really is supposed to be a set of tools that's not particular to manipulation, but we are using it in this case, that is built on ROS2 and really made to take a lot of existing open source components that are wrapped in a way to make them modular per the standards and guidelines we have developed, but also so that others using it can drop in their modifications and custom modules. With this, there's a series of guidelines we're developing that hopefully we'll get some insight from this workshop, such as, for example, every grass planning algorithm behaves as a service, utilizes the same request and response message type, such as image in, pose out. And this will depend on the particulars of your grasping algorithm, but just kind of an example. And we're also intending for this to be as hardware agnostic as possible. Of course, we're still in the kind of ROS2 transition phase, a lot of hardware not currently supported, so there's a lot of assumptions being made there. The kind of prior work for this was actually a lot of development in ROS1, utilizing FlexB state machines, which made it really easy to make things very modular, kind of change the flow of experiments, but not incredibly flexible. So now moving into ROS2, we don't have the same kind of GUI that we had available with something like FlexB, but given that we're building this from the ground up, more with a focus on modularity this time around, it is going to be, we think, a much more fruitful system. I will also just give a fair warning that I am not the technical developer of this. It's one of my staff members, so I'm going to spout some technical jargon that I'm not going to be able to answer a whole lot of questions about. But just as kind of a look back into some of the experiments that we've done in the past to kind of get us here, was starting with using the FlexB state machine to compare the performance of a grasp planner like GPD across a couple different embodiments. Then expanding that into some automated hardware to make grasp execution repeatable, for repetitions. And then very recently doing a study across 2 different labs with 2 different robots, 4 different grasp planners, and evaluating their performance therein, all under this common pipeline. So these are a lot of those technical details into how that infrastructure is put together. We've used the word template and recipe a lot today, and I think that's kind of the notion that we want to stick to. Things that we can follow that are modifiable and can be dropped in and out. A lot of these technical details I'm not going to spend a whole lot of time on, but suffice it to say that we are trying to develop this so that the different elements of those pipelines can be easily pushed in and out. And on the grass planning side, so I was talking about these kinds of guidelines that we want to develop to make this pipeline, actionable. What we've started to look at is, of all of the different kind of grass planning algorithms that fit our use case, which right now we're looking at a very basic kind of picking and clutter, if we start to investigate each of these algorithms and categorize them in terms of the type of input data that they take and typically what their output pose is used for, can we start to identify these commonalities and then maybe develop a guideline that can make them modular per the type of grass planner? So for all of these that take in point clouds and output a 6-degree of freedom pose, there's probably a pretty standard interface that we could use to make them modular per our pipeline. And to throw in back another plug for robotmanipulation.org, we actually use this repository we've set up to make this down selection easier. So on this website, we have a handful of these different repositories. This is just the one for grass planners as of about a month ago, where we've been constantly updating, grabbing different grass planners from the research space. They're all organized by some of these parameters, like what type of input data do they take, how do they output their pose. And we first developed this as, one, so we can investigate the space ourselves, but also so that other users of the repository can find something that fits for their pipeline. We're now using this resource and continuing to update it so that we can come up with, let's say, 3 to 5 kind of types of grass planners, motion planners, perception modules, whatever they might be, and hopefully develop some sort of standard or guideline around it so that they can be interchangeable within this pipeline. And I think Kostas is going to talk a bit more about the kind of the benchmarking aspects of robot manipulation later today. So we have started to use this pipeline again, our ROS1 version, in a paper that is currently under review, but available on archive, where we took these 4 fairly old, vision-based, top-down, camera-based grass planners, integrated them in a common pipeline, and evaluated them across 2 labs, 2 robots, so 2 different embodiments in sim and physically. And it was really easy to conduct this benchmarking because we had this common pipeline to swap them between. And this is not our work, but the Scene Replica project out of UT Dallas is another example of kind of this type of methodology being utilized elsewhere. Now, to my knowledge, this group is not using necessarily, this built from the ground up modular pipeline to conduct their benchmarking, but they've done all of this benchmarking where they change out perception, grass planning, motion planning, in order to compare and contrast all of their methods together. So what this is at least encouraging to see is that this mindset of making things modular and interoperable to improve benchmarking is not something that is unique to us, and that we're happy to see this kind of being done throughout the space. We're going to take this a step further in the next couple of months, where we are going to be holding a hackathon at the Nerve Center at UMass Lowell, where we have a set of diverse robot arms. We're taking this pipeline that as it continues to get developed, and we're going to be integrating something like 10 to 20 different grasping pipelines, maybe some other elements as well, and doing a lot of side-by-side benchmarking with them. One, as an exercise of the pipeline itself, but really to try to convene on what this kind of guideline or standard might be, in addition to doing a whole bunch of benchmarking that will make for, I'm sure, a great set of journal papers. So hopefully the next time you see me briefing on this project, I'll be talking about the results of that. That's where I'm going to pause. This is just, again, a look into kind of how the Compare product is trying to solve some of these things. And happy to take any questions before we go into our breakout section. Thank you. Yes.
One of the things we just heard about was how message passing, et cetera, becomes part of the bottleneck and the concern in terms of how do you get high throughput, et cetera. By design, this looks like it's set up to deliberately isolate things such that they're modular, et cetera, but that also means that you're passing messages by design very frequently. If you didn't do that, you'd have to deal with overlapping PIP requirements, et cetera, all of that dependency hell. How are you guys thinking about approaching isolated runtime environments versus for modularity versus performance metrics that are time-based, et cetera?
Yeah, this is a very good question, and I will say that it is currently an open question in that there's kind of I'd say there's two, not audiences, because they certainly overlap. On the one hand, we want to make it easier for people to integrate open source components and contribute open source components that can be integrated. So by making them modular, we're hopefully, reducing the barrier to doing that. Understanding that it does introduce these, limitations in runtime, execution, et cetera. I would say that this first kind of exercise into this area it's really just that. And I think there's a lot more for us to explore where we're not trying to deliberately isolate everything, but we do know that in at least a lot of the prior research and current research that is not focusing on, say, a learning-based like end-to-end solution, they typically are, leveraging existing open source and trying to integrate it for their new algorithm that they have to run. So by making it modular, we're hoping to ease that burden. So it's still an open question. And I hope I'm not totally dancing around answering it, but yeah. Yes?
I have more practical questions, mostly regards to how do we make fair comparisons, etc., especially for publishing papers. So, for example, in the example you shared with the different modules for grasping, that you have all these different methods, right? So, how do you ensure that the comparison is fair if these methods have been trained in different data sets, if these methods have been different architectures, right? How are you thinking about this problem?
So if we leverage any of the existing benchmarking protocols, so the one I reference here from Becca Roglu, who will be actually speaking later today, this is a very basic but holistic evaluation. It's very task-based sets of metrics that are really based on the performance of the task, success and failure of the grasp, of the pick and place, et cetera. For some of the additional metrics that get more into this kind of component level, like how accurately did your grasp planner select, a successful grasp, or how much data was it trained on? There's a lot more for us to uncover there. I would expect that in the same way we're trying to approach maybe some common or standard interfaces for the types of grasp planners, there may also be particular metrics that correlate to those types of grasp planners that we also want to try to standardize on. If something is ingesting only point clouds versus something that's only ingesting 2D images, there's probably a different set of metrics we need to apply. So it's something we're certainly aware of, but through these kinds of community exchanges is where we want to try to explore that. Again, I'm not trying to cop out of any of these answers, but yeah.